Let's take a look here at this example. You have a 4-meter long, 500 kilogram steel beam. It's uniform so that the mass is evenly distributed. And it is supported at 1.2 meters from the right end. What is the gravitational torque about the support? So it's like a seesaw. You have a beam here. And it's supported at 1.2, so from the right. So this is 1 meter. So 1.2 would be somewhere here. So it's supported here by like some kind of a pivot. So you can imagine what happens to the beam. It would just fall. It would just fall. So let me show you here. This is not 4 meters, but imagine if I have the beam like this and it is just supported here, it will just fall. It will just fall off. Why does it rotate? Well, the answer is because there is the gravitational force. In fact, there are two forces here. It's in contact with the beam, so the beam will apply a normal force upward. And then there is the gravitational force, the force of gravity. Remember, the net force on an object acts as if what? As if the whole force is acting at the center of mass. So here is the center of mass. And so the net external force here, you would have two forces, one of them from the support and one of them is from the force of gravity. And the force of gravity is mg. That's the force of gravity, is mg. Now, how much torque? When you say calculate the torque, you have to ask about what point, because to calculate the torque, you have to know how much force you're applying, where you're applying the force, and in what direction relative to the distance from the pivot point. So I would call this one here the force from the pivot point. So what is the torque due to the pivot point? They didn't ask for it, but let me just calculate it. Solution. We'll get to it also when we do static equilibrium. The torque due to the pivot point about the pivot point, well, it would be the force of, would be R to the pivot point times the force from the pivot point times the angle that they make with each other. But how far is the force from the pivot point to the pivot point? Well, it's at the pivot point, so this part here is 0, so this whole thing will become 0. So this doesn't contribute anything to the torque about the pivot point. How much torque does the gravity contribute? So the torque due to gravity, I will call it tau due to g, will be the distance from the pivot point to the center of mass, which is this distance here. We have r. I will call it r to the center of mass. R to the center of mass. Times the force itself, the force of gravity, times the sine of phi. Let's try to decipher this. Well, let's see. Torque due to gravity. First of all, would it be positive or negative? Well, gravity is trying to spin the beam counterclockwise. We can use that cross product thing with the vectors and so on, but it's unnecessary. It's clear that it will cause counterclockwise. How far is it? Well, this is 2 meters. From here to here is 1.2. So how much is left? From here all the way to the end, this is halfway. That's 2 meters. If this is 1.2, this part here is 0.8. So it will be 0.8. And we already decided that it's positive torque. The force of gravity is mg. But the mass is 500 kilograms times 9.8. So 500 kilograms times 9.8. This is the force. Both of these is the force. Times the sine of phi. Sine of what? Well, r is a vector that points from here to the point of rotation. So r is pointing in this direction. And f is this way. So they make a 90-degree angle with each other. And so that is 90 degrees. And sine of 90 is 1. And so you multiply these, and you get the torque due to gravity will be, well, let's calculate it. 500 times 9.8. 500 times 9.8 times 0.8. That gives me 3920. Meters times newtons, or newtons times meters. Okay. Let me just make sure I have the right answer. Yes, we do have the right answer, so that's good. Now, why do we define the torque the way we define it? I mean, it's all handy and all to tell you about something that you have to put the door hinges somewhere and so on. But is that enough? I mean, maybe. But the reason we do it is we want to get what we call Newton's second law for rotational motion. We know Newton's second law for linear motion. It's F equal to ma. And you might guess, if you remember, let me just write it again. You have, instead of x, you have theta. Instead of linear velocity, you have omega. Instead of regular acceleration, you have alpha. The tangential acceleration, you have alpha. And instead of mass, you have the moment of inertia. And we learned about that. And now, instead of force, what do we have? Well, the counterpart will be the torque. And just how we had F equal to ma, well, you can guess. Instead of mass, you have I, and instead of A, you have alpha. And so you have I alpha. That's what we want to get. So to do that, let me just show you what we'll do. So imagine you have a really light rod here, and this is a mass M. And let's say you can have many forces, but the net force on it, let me call this here, the distance from here to here is R, and I'm going to apply a force this way. My force is this way. Right? That's just the net force, and it's understood to be the net force, and it's just the perpendicular part of the net force. Any parallel part will not cause a rotation because there is a pivot here. If you apply a force this way, the pivot will apply a force back on you and will cancel that. This part is the n-cancelled part. So it's just understood. That's just the perpendicular part. What happens? Well, the mass will rotate. So imagine the mass here would have some initial velocity. Maybe it was moving. And then a little bit later, it will turn by an angle delta theta here, delta theta. And so the force is always being perpendicular, so it's still being applied. So it has been applied over this arc length here. And how long is the arc length? Is delta S. So how much work did this force do? Well, it's just parallel to the displacement. It's perpendicular to this, but it's parallel to the arc length. So the work done by the force is just the force times the displacement, delta S. But delta S is R times delta theta, just from geometry, R times delta theta. And so that's that. And remember the work energy, I will replace it in a moment by R delta theta. But remember from the work energy theorem that R delta theta, the work done is equal to the change in kinetic energy. And F delta S is, and here delta theta is a really tiny change. It's after one moment in time. So F times delta S will be R times delta theta. That's what I have on the left-hand side. On the right-hand side, I have the change in kinetic energy. Remember, kinetic energy, you can write it as 1/2 mv squared for the point mass, or you can write it as 1/2 I alpha squared, 1/2 I omega squared. Because, let me write it as 1/2 mv final squared minus 1/2 mv initial squared. I think it's worth reminding you of the moment of inertia and how it worked. And remember, v is equal to r times omega. So r is fixed, but so v initial is r times omega, the angular velocity at this point. And then here, v final will be r times omega final here. And so I would have, first of all, F times R here is what we call the torque. That's how we define the torque, was F times R times the sine of theta. But F here is already perpendicular, so it's just F times R. So that's the torque part. And here I have delta theta. Here I have 1/2 of the mass times omega final squared will be R times omega final, and you square it, so you just got R squared omega final squared, and then minus V initial will be R omega initial, but you square them, you get R squared omega initial squared. And let's factor the R squared. So you get tau delta theta will equal to 1/2 mr squared times omega final squared minus omega initial squared. Omega initial squared. And for a point mass, at distance r from the point of rotation, the moment of inertia is mr squared. So this part here is the moment of inertia for that particular mass. If you have more masses, you can just sum them. So, and if you have more forces, this will be just the net torque. So you have tau delta theta would be 1/2 I, so this whole thing became I. Now omega final squared minus omega initial squared, if you remember from kinematics, it was 2 alpha theta final minus theta initial, right? Remember from kinematics, omega final squared minus omega initial squared would be 2 alpha theta final minus theta initial minus theta initial. This is delta theta. So I'm going to replace omega final squared minus omega initial squared by 2 alpha delta theta. So this will be 2 times alpha delta theta. And the 2 and the 1/2 cancels. And the delta theta and the delta theta also cancels. And I have tau is equal to I alpha. So this gives me the nice form for Newton's second law for rotational motion. And that's really why we define the torque the way we do, because it will give us a nice transition from rotational to, or linear to rotational motion. A nice, what we call dictionary. Okay. In a moment, we will see that, remember for the regular momentum, it was mass times velocity. Mass times velocity. Let me write it this way. For angular, we will have, instead of linear momentum, we will have what's called angular momentum. We'll have to give it a symbol. I'll put a question mark here for the symbol, and it will be I times omega. Instead of mass, you have I, and instead of instead of V, you have omega. The strict definition of the angular momentum will be the cross product of R and P, but we'll worry about that also later. Okay, so I would like us to look at this problem here. It says, far in outer space, a 100,000 kilogram rocket and a 200,000 kilogram rocket are docked at opposite ends of a motionless 90-meter long connecting tunnel. It looks like this. So they're connected by something rigid. You have M1 and you have M2. All right? So let's call this is M2 and this will be M1. Okay, sounds good. So they're connected by a 90-meter long connecting tunnel. The tunnel is rigid, meaning its length cannot be changed. And it can bend and so on. And its mass is much less than that of either rocket, meaning ignore the mass of the connecting tunnel. The rockets start their engines simultaneously, each generating 50,000 newtons of thrust is in opposite directions, not is, in opposite directions. So this one will generate thrust this way, and this one will generate thrust this way, force F, and this one will also generate thrust of force F in opposite directions. What is the structure's angular velocity after 30 seconds? Well, notice here, our system will be M1, M2, and the tunnel, the two rockets and the tunnel. And we ask, what is the net external force on them? Well, there is force on this one, and there is force on this way. But the net external force, since these two forces are in opposite directions, the net external force is 0. If the net external force is equal to 0, it means the center of mass cannot accelerate. So the center of mass will be somewhere here. It will be biased toward the heavier rocket, and the center of mass is not going to move. The two rockets will spin, but the center of mass will not move. Remember how we defined the center of mass. It was that we looked at different masses, and we said if the internal forces between the masses don't matter, only the net external force will change the acceleration of the center of mass. In this case, the external force, there is an external force of 50,000 newtons this way, and there is an external force of 50,000 newtons that way. So the net external force is 0. If you add them, you get 0. There are just two vectors in opposite directions. But that doesn't mean if the net external force is 0, it only means that the center of mass is not going to move. It does not mean the rockets themselves are not going to move. They will start spinning. In fact, the torque is not 0. This will generate a counterclockwise torque, and this one is also generating a counterclockwise torque about the center of mass. So what we will do is, since they will spin, we have to calculate the location of the center of mass. And I don't know why I drew it at an angle. Let me draw it horizontal so that it would be nicer. And then we will find the moment of inertia about this center of mass, and then we will use Newton's second law in the form that tau equal to I alpha to figure out what the acceleration about the center of mass is, and then use kinematics to figure out what the angular velocity is after 30 seconds. So let me just draw this. Here is M1, and here is M2. Well, I'm sorry, here is M1, and here is M2. Let's do them in order, M2. And I'm going to call this my x-axis. This one will be at the origin, the location of this one. So x1 is equal to 0, and this is the location of this one. x2 is equal to, well, how far are they apart? I think they're 90 meters. Yeah, that's 90 meters. x2 is 90 meters. And I would like to find out where the center of mass is. It will be biased toward M2. It will be somewhere here. By definition, the center of mass, x center of mass, will be M1. I like this problem because it reviews how to calculate the center of mass and then how to calculate the moment of inertia with respect to some point, to some axis of rotation, and then it will combine it with what we learned today, or right now. So M1 x1 plus M2 x2 divided by M1 plus M2. And so x center of mass will be, well, it will be what? M1 x1, x1 is 0, so this part here is 0. So, and then M2 x2, M2 is 200,000 times 90 meters, x2 is 90, divided by the total mass, which is 100,000 plus 200,000, that's 300,000. And the good thing is all these zeros will go away. And 90 divided by 3 is 30, and 30 times 2 is 60. So x center of mass will be at 60 meters. 60. So the center of mass will be here at 60 meters. Meaning, where's my red pen? Here it is. Meaning, the distance from here, so they would be spinning about this axis. They will be spinning like that, because this force will be this way, and there will be a force here this way. So they would be spinning about that axis. And so this one here, this distance, let me call it R1. The whole thing is 90. This is 60. And so R2 here is 30 meters. So we found the center of mass. Now that we need to calculate the moment of inertia, and we will calculate the moment of inertia about the axis around which they will rotate, and they will rotate about the center of mass, and we came to that conclusion because the net force is equal to 0, so the center of mass is not going to move, even if they will rotate. So let's calculate the moment of inertia about the center of mass. Remember, by definition, the moment of inertia will be m1 r1 squared plus m2 r2 squared. So the moment of inertia about the center of mass for our problem will be m1 is 100,000, r1 is 60, but you have to square it. Don't forget to do that. And then m2 is 200,000, and r2 is 30 squared. R2 is 30. So we get the moment of inertia will be, well, we have to calculate that. That will be a very large number. I think you get like 540 million. 100,000, yeah, about 540 million. I think I would just write that down, 540 million. And of course the units are kilogram meters squared. It's a moment of inertia. Okay, okay, sounds good. And we have now we found the moment of inertia. We need to calculate the torque. So the torque due to F1 tau 1 will be R1 F1 times the sine of the angle phi 1. Now again, it will cause counterclockwise torque, so the torque will be positive. Right? Imagine you fix this and push the axis this way, so that the mass will spin this way. It's like, again, with my meter stick, you're fixing it at here. This one is trying to rotate it this way, and this mass is pushing it, the thrust is this way, so it's also rotating like that. So it's both are counterclockwise, so both are positive. And by definition, torque is RF sine theta. And the angles are all 90 degrees. This is 90, and this is 90. And remember, R is the vector that points from the point of rotation to where the force is applied. The force is here, so R is the distance from here to here, and its direction is this way. So it's at 90 degrees anyways. So R is 60 meters for F1, for the first force, and the first force is 50,000 newtons. 50,000 newtons. And the sine of 90 is 1. So it will be 6 times 5 is 30. And then I have a 0 from here, and then 4 zeros from the other one. I think I have it right. It's about 3 million. And tau 2 will be R2 F2 sine phi 2. And then R2 is, well, this one is 30 meters away. And the force is still 50,000 newtons. So this would be 150, let me see here, 3 6 zeros. So 1, 2, 3, 4, 5, 6. I think that looks good. So the total torque, tau total, or net torque, the net torque, will be, well, you just add them. 3 million plus 1.5 million, and you get 4.5 million, like that, Newton meters. Let me just double check that I have it corrected. I want to make a mistake all the way at the very end. Yeah, that looks good. Okay, they want the angle, or they want omega. So what I'm going to say is that the net torque is I alpha. So again, you can go back to Newton's second law in the linear form and then deal with the angles, or just use this one. It's easier. It's way easier too. That's why this formalism, or this way of doing it, was invented. So alpha will be the net torque divided by I. The net torque is 45 with like 5 zeros here. I want to make a mistake there. And then that one is 540 million for alpha. 540 million. I'm sorry, for the moment of inertia. So take 5 zeros out. Take 5 zeros out. And then divide. So you get alpha. So you get alpha. I will just get the number also. Write it down. It's 0.00833. 0.00833 radians per second squared. And now we can figure out what the angular velocity is after 30 seconds? Well, it's constant angular acceleration, so we have omega final will equal to omega initial plus alpha times the time. They started from rest, as they said, so omega initial is 0, alpha is 0.00833 times the time, that's 30 seconds. 30 seconds. I would imagine when you multiply by 30, you get a nice number. So omega would be, let me just also quote that, it's 0.25 radians per second. Okay, 0.25 radians per second. I think this is a nice problem. It's worth practicing. You should check it out. It's in our book, and our book is Randall Knight, right? Physics for Scientists and Engineers, and it's problem 12.10, example 12.10 from chapter 12. All right, we will get to, I have to pause this one because we'll get into the 30-minute mark and then start the next video where we do a couple more problems and we do static equilibrium also.